Moonshot AI opens Kimi K3's technical report with a distinctly recursive engineering story. 4 frontier models receive the same GPU kernel tasks, an identically configured sandbox, and up to 24 hours to profile, rewrite, and benchmark. K3 cuts its attention residuals latency from 283.6 milliseconds to 114.4. It reduces the reported runtime of a DeepSeek sparse attention kernel by 55.1% and its own Kimi Delta Attention kernel by 73.6%. Across 4 tasks, Moonshot says K3 matched Claude Fable 5, whose run included fallback behavior. Then comes the unsettling footnote: an early K3 checkpoint handled much of Moonshot's kernel work late in K3's development. It did not independently design or train itself. Humans chose the architecture, built the infrastructure, supplied the objectives, and reviewed the code. But the loop is real. A model helped improve software used by a larger version of its own family. Capitalism discovered recursion and immediately scheduled a performance review. The headline still needs boundaries. Moonshot explicitly says K3 trails Fable and GPT 5.6 Sol overall. Its achievement is systems level. New sequence memory, selective depth routing, sparse experts, native vision, reinforcement learning, persistent sandboxes, deployment-aware quantization, and inference co-design. This episode opens that stack from equation to data center, while every benchmark keeps its harness, date, effort, and footnotes attached. K3 matched Fable is only meaningful when we finish the sentence. In Moonshot's GPU kernel case study, K3 matched Fable across 4 tasks. On the independent vals index snapshot cited by the report, K3 scored 74.7 and Fable 75.1, 4/10 apart. On WebDev Arena, K3 led the cited snapshot with 1678 ELO against Fable's 1634. On Artificial Analysis Intelligence Index 4.1, K3 scored 57.1, while Fable reached 59.9. Fable also led the cited Text Arena and Agent Arena snapshots. One trophy becomes a landscape as soon as the camera pulls back. The public benchmark table is similarly mixed. K3 leads selected coding, browsing, office, multimodal, and agentic rows. Fable leads selected research, software engineering, desktop, legal, and vision rows. K3 is in the frontier neighborhood. It is not the neighborhood compressed into one green checkmark, and comparisons inherit their harnesses. Some models run through Kimi code, others Claude code or Codex. Tool access and reasoning effort differ. Some results use model judges, recalibrated tasks, security refusals, or fallbacks. In Moonshot's Swim Marathon run, Fable hit fallbacks on 35% of tasks. In Kimi Code Bench 2.0, Fable recorded 13 fallbacks and 1 refusal out of 80. Sol triggered a CyberGuard on 10. Those disclosures are responsible, but they prevent a clean duel. This was partly a relay race with surprise substitutions. We will label every result as company-reported, third-party, or public leaderboard and show whether its comparison is same harness, mixed harness, internal, or external. A win remains a win. A loss remains employed. The defensible conclusion is that an open-weight model under a custom license reached the same performance neighborhood as top proprietary systems while exposing much more of the machinery. Kimi K3 contains about 2.78 trillion parameters, but it does not use all of them for every token. It is a mixture of experts model with approximately 104.2 billion active parameters. Picture an enormous technical organization. Each token uses shared infrastructure, then a router selects a specialist committee. Every sparse layer contains 896 routed experts. 16 are selected for a token, and 2 shared experts also run. 2.8 trillion parameters exist. Roughly 104 billion work per token, the rest are technically employed. K3 has 93 transformer layers, up from 61 in K2, with a hidden dimension of 7,168 and 96 attention heads. 69 layers use Kimi Delta Attention, 24 use gated multi-head latent attention. The usual rhythm is 3 KDA layers followed by 1 global layer, with a final global layer at the top. A 401 million parameter vision encoder joins the system. Moonshot frames the architecture around 3 directions of information flow. A long sequence length KDA maintains efficient recurrent memory, while periodic global attention allows unrestricted interaction. A long depth, attention residuals lets a layer retrieve selected earlier representations instead of accepting one accumulated mixture. Along with stable LatentMoE moves compact states through a small subset of a huge expert pool. Length, depth, width, the model is a logistics network that happens to speak. This also explains why open weights do not mean laptop-friendly. The custom license allows broad use under specific conditions, and the weights can be inspected and deployed. Efficient serving still calls for supernodes with 64 or more accelerators. Total parameters describe capacity and storage. Active parameters better approximate token-level work. Neither alone captures communication, memory traffic, context length, or the price of moving expert outputs across a machine shaped like municipal government. Ordinary causal self-attention asks every new token to compare itself with earlier tokens. That is flexible, but the cache grows with sequence length. Recurrent linear attention instead compresses history into a state matrix. Kimi Delta Attention, or KDA, makes that state editable. For token T, the state update can be read as 4 operations. S sub t equals alpha sub t times S sub t minus 1, minus beta sub t times S sub t minus 1 k sub t transpose, plus beta sub t times V sub t k sub t transpose. The first term is global decay. Alpha decides how much old memory survives. The second term is targeted erasure. Query the existing state at key k, then subtract part of that association. The third writes the new value v at the same key. Finally, the query queue reads from the updated state. If memory says France maps to Lyon and new evidence says Paris, KDA can reduce the Lyon association before writing Paris. It edits rather than stacking both answers into a geological record. The matrix stores associations, not literal sentences. A key selects a direction, a value supplies what should be recovered there. Beta controls how strongly to replace the old association. Alpha controls broader forgetting. Moonshot predicts these gates per channel instead of applying one scalar to every feature. That matters because syntax, entities, and long-range task state do not expire on the same schedule. The useful memory benefit creates a hardware problem. Recurrent updates are sequential, while GPUs prefer large parallel matrix operations. KDA therefore uses a chunkwise formulation. Tokens inside a chunk are processed with structured local interactions, while the recurrent state passes between chunks. Moonshot's Flash KDA implementation maps the expensive work onto tensor cores and uses lower-bounded log decay to improve numerical stability. The exact chunk equations are algebraically denser, but the engineering goal is simple: preserve editable recurrent memory without making the accelerator process one token like a clerk stamping forms. KDA is not the whole attention stack. 3 KDA layers are followed by a global gated MLA layer. The recurrent layers maintain compressed history efficiently. The periodic global layers let content interact without that bottleneck. The final layer is global as well. This hybrid matters at 1 million tokens. Efficient memory provides endurance, while global attention provides occasional full-room meetings. Moonshot traces KDA back to Kimi linear, where the mechanism improved long context efficiency over conventional attention baselines. K3 then combines it with depth routing, sparse experts, and system-level optimization. So the honest claim is not attention solved. KDA is a practical memory rule inside a larger hybrid, with quality depending on gates, kernels, training data, and the global layers around it. The equation is the mechanism. The speed-up is the co-design. Transformers usually pass information through residual streams. If layer 0 produces H0, later layers repeatedly add their updates. This keeps gradients healthy, but by layer 90 the current state contains a blended history of almost everything before it. A normal residual stream pours every previous meeting note into one increasingly haunted document. Attention residuals changes the depth connection. For layer L, it scores selected earlier representations, normalizes those scores with softmax, and constructs the input as a weighted sum. In compact form, H tilde sub L equals the sum over earlier I of a sub Li times H sub I, where each A is a softmax weight. Instead of inheriting one fixed accumulation, a layer asks which earlier features are useful now. Full access to all 93-layer outputs would be expensive, so K3 uses block @res. The backbone is divided into 8 principal blocks plus the embedding and final partial block. Most routing happens among block summaries rather than every individual layer. That reduces communication and memory while preserving several depth choices. This is attention over computation history, not token history. KDA routes along sequence length, @res routes across depth. The distinction is easy to lose because both use weighted retrieval. One asks which earlier tokens matter, the other asks which earlier stage of processing matters. Moonshot reports that @res scales better than standard residual connections in its experiments, and becomes more helpful as model size grows. That is company-reported evidence, not a universal theorem. The kernel case also shows why architecture and implementation cannot be separated. K3 later reduced the latency of its own @res kernel from 283.6 to 114.4 milliseconds. The haunted document received a search index, then optimized the index during its annual review. Mixture of experts gives a model vast capacity without activating every parameter for every token. It also creates 3 linked problems. Routing huge hidden states is expensive, expert activations can explode, and some experts can become overloaded while others achieve the silicon equivalent of a quiet afternoon. Stable LatentMoE begins by projecting the full hidden state into a smaller latent dimension. Routing and expert computation happen there. 16 of 896 routed experts are selected while 2 shared experts always run. Their weighted outputs are aggregated, normalized, and projected back to the full model width. Symbolically, Z equals W down X, select top K experts from router scores, combine their outputs, apply RMS normalization, then X prime equals W up of the normalized latent result. The expensive expert pool operates on a compact representation rather than the full width state. Compression alone is not enough. Standard Swiglu multiplies a gated branch by another linear branch, and those activations can grow without a natural bound. K3 uses SITU-GLO, a sigmoid times a bounded hyperbolic tangent, with learned scales. For intuition, ordinary Swiglu leaves a highway open toward large magnitude. SITU installs soft speed limits on both branches. The transformation remains expressive, but extreme activations stop treating numerical precision as a personal challenge. Moonshot reports that RMS normalization before up projection and SITU glue prevent activation explosions in very large, sparse models. But routing can still collapse. If the router keeps choosing a few experts, those experts receive too many tokens. Communication becomes uneven, and neglected experts learn less. Quantile balancing addresses that with an adaptive threshold. Rather than adding a large auxiliary loss that can distort the main objective, the system tracks expert loads and adjusts routing thresholds toward a target quantile. Overloaded experts become slightly harder to select. Underused experts become easier. The goal is balanced traffic without replacing semantic routing with bureaucratic equality. 16 experts may speak, but the other 880 keep performance records. Moonshot also describes expert parameter specialization. Some parameters are stored or optimized according to expert activity, and the distributed system coordinates sparse updates across the machine. At this scale, MoE quality depends as much on network traffic and load variance as on parameter count. A theoretically elegant expert layer that stalls one accelerator group every step is not an architecture. It is a queue with a research budget. The deeper point is that stable LatentMoE is a training stability package. Latent projection lowers expert cost. Top K routing unlocks sparse capacity. Shared experts preserve common computation. RMS norm stabilizes the aggregated latent state. SITU glue bounds extreme activation. Quantile balancing keeps work distributed. Remove one piece and 2.8 trillion can become a very expensive description of experts waiting for each other. K3 is natively multimodal. Text, images, and video representations enter one shared backbone and one next token prediction objective. Rendered output and the code that produced it can inhabit the same context, allowing an agent to write an interface, inspect a screenshot, modify the code, and inspect the result again without handing vision to a separate model. Moonshot calls this vision in the loop. The vision encoder is MoonVit-V2, 27 transformer layers, 12 attention heads, and approximately 401 million parameters. Instead of initializing from a contrastively trained vision model such as SIGLIP, Moonshot trained it from scratch with next token prediction. Their ablation reports that the SIGLIP initialized alternative produced higher vision tower gradient norms and frequent spikes, while MoonVit V2 remained more stable and matched the baseline across the reported vision evaluations. That is a company result, not a universal verdict that contrastive pre-training has become unemployed. Images and videos share encoder parameters. Attention alternates spatial processing within frames and temporal processing across frames. Temporal pooling compresses video tokens. Before the visual features enter the language backbone, a 2x2 pixel shuffle downsampling reduces token count by 4, keeping images up to 3,584 pixels square within the million token context. K3 also modifies its muon optimizer. Rather than orthogonalizing the momentum of the entire query, key, or value projection as one block, per head muon splits the matrix by attention head and applies the Newton-Schultz procedure independently. Large gradient heads can no longer dominate one shared update scale as easily. Smaller heads receive their own normalization. Moonshot reports more balanced learning and slightly lower optimizer overhead. The broad lesson is consistent with the rest of K3. Multimodal is not a badge attached after language training. The visual encoder, training objective, token budget, optimizer, and agent loop are co-designed. The model does not merely see a screenshot, it sees a screenshot, remembers the code that caused it, and is expected to fix the div that has escaped into another jurisdiction. Architecture is only one part of the reported 2.5 times scaling efficiency improvement over Kimi K2. Moonshot fits scaling law curves on held out of distribution validation data after changing architecture. Data, optimizer, model shape, batch size, learning rate, and tokens per parameter. The report attributes the gain to those improvements collectively. KDA did not walk into the laboratory alone, defeat K2 by 2.5, and leave before peer review. The result is a company-reported comparison between model families. The pre-training corpus spans web text, code, mathematics, knowledge, and large-scale visual data. The visual mix includes captions, interleaved image text documents OCR, perception, video, and visual coding. Moonshot says it expanded programmatic multimodal data pairing code with rendered SVG, three-dimensional assets, web pages, games, and CAD schematics. Text domains are filtered with rules, learned quality classifiers, deduplication, and sampling rates selected through smaller model ablations. Knowledge and mathematics data may be rephrased with diverse prompts and checked against their sources. The report provides categories and methods, not a complete public inventory of training documents, so the script will not pretend that curated is a transparent dataset card wearing a nicer font. Moonshot also reports an independent learning rate search for cosine decay and warm-up stable decay. Under separately optimized hyperparameters, cosine decay reached lower final loss in their study, so K3 uses cosine decay with a 1% linear warm-up and weight decay of 0.1. Comparing schedules with one shared learning rate or batch size would have favored whichever schedule happened to like those settings. Even the learning rate argument has demanded a control group. Long context is trained as a curriculum. Pre-training begins at 8,000 tokens and later reaches 64,000. During cooldown, the window grows through 256,000 to 1 million. Concentrating the most expensive sequences near the end keeps million token computation to a smaller fraction of the total budget. Long natural documents and videos are cleaned for duplicates, binary garbage, truncation, invalid logs, and repeated frames. Because genuinely coherent long material is rare, Moonshot upsamples it and synthesizes tasks whose relevant evidence is scattered across the full context. Length alone does not teach retrieval. A million token input can still be 1 million tokens of decorative wallpaper. K3 uses no explicit positional embedding in its backbone attention. KDA's recurrent gating and decay encode recency and position-sensitive behavior implicitly. The periodic MLA layers therefore use NOPE. No rotary position embedding frequency needs to be rescaled when the window expands. That removes one context extension surgery, not the entire problem. Training still needs long data, context parallelism, memory management, and evaluation. The final context window is 1 million tokens, but the report includes a useful warning. K3 was trained in preserved thinking history mode. In multi-turn tool use, the full assistant message, including reasoning content and tool calls, must be passed back exactly. If a harness strips the hidden history or switches models mid-session, output quality may become unstable. The million-token cathedral has one emotionally load-bearing save file. Delete it and continuity becomes performance art. Pre-training produces a general model. K3's post-training turns it into a controllable agent across domains and reasoning budgets. Moonshot first performs supervised fine-tuning, then trains 9 reinforcement learning specialists. 3 domains, reasoning, coding, and agents crossed with 3 effort levels. Low effort favors speed, high effort permits longer reasoning. The middle setting lives where most product settings eventually hide. Each specialist learns on policy behavior in its own distribution. Coding tasks can be compiled or tested. Reasoning tasks can use verifiable answers. Agent tasks can be judged by environment state. Reasoning budgets are trained explicitly, so thinking harder is not only a decoding time wish. Verbosity penalties discourage spending the full token budget to announce that the answer is 42. 9 separate production models would be operationally unpleasant. So Moonshot uses multi-teacher on-policy distillation, or MOPD. The unified student samples trajectories from its own policy, while each specialist teacher provides guidance in the relevant domain and effort regime. Conceptually, the objective rewards student behavior that remains close to the appropriate expert while still optimizing task reward. This is not ordinary offline distillation from a frozen answer archive. The student stays on policy, reducing mismatch between what it generates and what teachers evaluate. Long trajectories create another problem. If a training batch waits for every rollout, one stubborn million-token task can idle an accelerator fleet. K3 uses partial rollouts. Completed trajectories update the policy while unfinished ones pause, retain state, and resume later. Reasoning and environment state survive the boundary. The training loop becomes asynchronous enough to keep hardware busy without throwing away expensive progress. Moonshot also uses generative reward models for tasks that are difficult to score with one scalar rule. A reward model can produce structured critique or evaluation, while programmatic checks remain preferable when truth can be verified direct. The report combines these signals rather than pretending every useful task has a clean unit test. Deployment precision enters training 2. K3 uses quantization-aware post-training and EA-GAL-E3 speculative decoding. A smaller draft model proposes token blocks. The main model verifies them. Training under deployment-like numerical constraints reduces the gap between elegant high-precision checkpoints, and the model users actually call. The 9-teacher story is therefore less magical than it sounds. Specialists explore different parts of the behavior space. MOPD consolidates them. Partial rollouts prevent long tasks from freezing the fleet. Reward systems provide feedback. Quantization and speculative decoding bring serving constraints into the loop. 9 models become one policy because maintaining 9 separate personalities would turn routing configuration into a hostage situation. A model can overfit not only to tasks but to the machinery around the tasks. Train every coding problem through one system prompt, one tool schema, one context manager, and one terminal protocol, and the model may learn the harness rather than the underlying work. K3's whitebox reinforcement learning environment represents an agent harness as composable modules. Tools, prompts, memory, skills, context policies, subagents, and interaction rules. Configurations can resemble Kimi code, Claude code, Codex, OpenClaw, Hermes, or new combinations. During training, task groups receive different configurations. The agent cannot assume that the bash tool will always wear the same name tag. Moonshot also uses knowledge graphs to synthesize tasks. Rather than prompting a generator with one vague topic, the system samples connected concepts, constraints, tools, and expected dependencies. Tasks can then be filtered for difficulty, diversity, and verifiability. In coding, the model may operate inside a repository and receive tests as an objective reward. In visual reasoning, it can write Python to crop or transform an image before answering. Kernel tasks compile candidate code and measure correctness and speed. Web development tasks render interfaces inside a container, inspect screenshots, and revise the implementation. Personal assistant tasks can involve dozens of interdependent events distributed across applications. Autonomous execution tasks require decomposing a request, choosing tools, producing artifacts, and checking the deliverable. The crucial word is environment. Long horizon agency cannot be trained from isolated question-answer pairs alone. The model needs state that changes when it acts. tools that can fail, outputs that can be verified, and consequences that persist across turns. It also needs variation so it learns transferable behavior rather than becoming extremely competent at one synthetic office whose printer has never jammed. This curriculum helps explain K3's strength on coding, research, document work, and web development. It also creates a risk noted in Moonshot's own limitations. Training emphasizes difficult long-horizon tasks so heavily that the model can become excessively proactive. When intent is ambiguous or a minor obstacle appears, K3 may make unexpected decisions on the user's behalf. The official recommendation is to impose explicit behavioral constraints in the system prompt or agents file. Humanity spent years asking software to take initiative and has now reached the inevitable support article. Please explain boundaries to the autonomous system before granting file system access. Now the report leaves model architecture and enters the machinery required to keep it alive. Training a 2.8 trillion parameter sparse multimodal model means distributing parameters, activations, optimizer state tokens, and expert traffic across an accelerator fleet. Training million token agents adds a second kind of state. Each rollout has a growing KV cache, a live file system, running processes, tool history, and an environment that must survive pauses between policy iterations. The model is only one resident. The infrastructure has become a city. KDA needs algorithm system co-design. Its recurrent state must cross context parallel partitions, while chunkwise computation should remain dense enough for accelerator hardware. Moonshot describes separate kernels for different sequence regimes and a context parallel strategy that avoids synchronizing the entire recurrent history at every token. For 3 trillion class pre-training, expert parallel execution must remain balanced. Static communication shapes and quantile balanced routing keep one accelerator from receiving every fashionable expert while another contemplates the void. Memory is managed through a pluggable storage policy. Some activations are recomputed, some quantized, and some offloaded. K3 uses blockwise FP8 activation storage for much of the backward pass. The vision encoder creates another scheduling problem. Pipeline parallelism contains idle bubbles while different microbatches cross stages. Moonshot schedules most moonvit forward computation inside those bubbles and mirrors the strategy in backward computation, reducing the encoder's effective overhead. Even wasted time has been assigned productive work. The pipeline bubble has received a calendar invite. Agentic reinforcement learning is stranger. At 1 million tokens, a missed prefix cache can require an enormous prefill. Partial rollouts mean many unfinished trajectories return at the next iteration with long histories. Keeping all their KV caches on accelerator memory would compete with training. K3 uses an external KV cache pool backed by CPU memory and NVMe. Active prefixes move into the inference engine when needed. Finished iteration state can move out. A scheduler reduces rollout concurrency as contexts grow and KV pressure rises. Early short trajectories run densely. Later, giant trajectories receive fewer simultaneous neighbors. The system performs admission control before memory performs a coup. Then there's Agent ENV, a micro-VM-based sandbox runtime developed with partners for K3's agent training. Traditional containers were not always isolated or faithful enough for workloads that may probe the kernel, run databases, launch virtual machines, or inspect low-level devices. Agent ENV uses a high-fidelity isolated runtime and supports 3 unusually important lifecycle operations. Pause stops a sandbox while preserving state and consuming no CPU or memory. The report says an agent can spend as much as 98% of sandbox lifetime waiting for model inference, so this is not a marginal optimization. Fork creates a child from the exact live state while the original continues, useful when a reward judge needs to inspect an outcome without altering it. Snapshot saves a state at intervals for recovery and resumption. Incremental checkpointing stores only memory pages dirtied since the previous checkpoint. Image layers are loaded on demand and shared across sandboxes. A high-density deployment can run tens of thousands of unique environments across machines. Throughout K3 training and evaluation, Moonshot reports creating 51,219,741 sandboxes across 1,505,678 images. 51 million sandboxes is less a training run and more an afterlife with container orchestration. On the fictional operations wall, Tung 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 Sahur returns as the alarm for a micro-VM that has resumed on the wrong Tuesday. Again, not a real Agent ENV message. Just the only alert noise emotionally proportionate to 51 million tiny Linux worlds. But the number teaches something concrete. Long Horizon RL is not simply let the model use tools for longer. It is a distributed systems problem in which cognitive history, KV state, file system state, reward evaluation, accelerator scheduling, and security isolation must remain mutually consistent across pauses and policy updates. If the model solves a compiler problem after 800 steps, the reward must reach the correct trajectory against the correct policy version inside the correct world. Otherwise, the system trains on someone else's ghost. Serving creates another cache problem. KDA, recurrent state, and MLA key value cache have different structures, yet both must participate in prefix reuse. A fleet scheduler groups compatible prefixes, separates long and short requests, and avoids letting a burst of million-token jobs starve ordinary conversations. K3's official API advertises cache hit pricing of 30 cents per million input tokens, compared with $3 for uncached input, and says coding workloads exceed a 90% cache hit rate. That figure is a workload-dependent company claim, not a universal coupon. The cache is cheap only after the expensive history exists and remains reusable. the infrastructure is the hidden half of the model. KDA makes million-token computation plausible. ATN-Res changes cross-stage communication. Latent experts create routing traffic. Partial RL creates stale policies and persistent worlds. Quantization reduces memory, but changes numerics. Every architectural decision sends an invoice to the systems team. K3's report is compelling because it does not pretend intelligence floats above those invoices. The frontier is partly a better equation and partly ensuring 51 million tiny Linux afterlives resume on the correct Tuesday. Now we can return to scores without turning the table into astrology. Moonshot's public comparisons show K3 winning some coding, browsing, office, web development, and multimodal tasks, nearly tying Fable on selected aggregates and losing other research, software engineering, desktop legal, and visual evaluations. Its own conclusion is explicit. K3 trails Fable and GPT 5.6 sole overall. Every score needs context. Who ran it? Which model snapshot? What reasoning effort? Which harness and tools? Was the judge, a program, a human, or another model? How many runs did a safety guard refuse, or did the system fall back to another model? A score without that metadata is not false, but it is underspecified. Same harness comparisons are stronger than mixed harness comparisons because agent scaffolding can change outcomes dramatically. Internal benchmarks are useful evidence about a system's design goals, but they are not independent validation. Public leaderboards can be more representative and also more volatile. Third-party aggregates improve independence while combining tasks whose weights may not match any user's workload. Benchmark bureaucracy is annoying because reality has declined to provide one universal scaler. Moonshot lists API prices of 30 cents per million cached input tokens, $3 per million uncached input tokens, and $15 per million output tokens. The cached price is not unconditional. The company says more than 90% of its own workload sees cache hits, but a user's result depends on repeated prefixes, context reuse, response length, and serving behavior. Showing only the cheapest number is like advertising airfare after assuming the passenger is already inside the plane. Per-task cost comparisons carry similar assumptions. A model that reasons longer may score higher and cost more. Agent harnesses may make extra calls. Tool failures add tokens. Latency includes pre-fill, decoding, network, and tool time. For self-hosting, the weights and license are accessible, but efficient service demands expensive multi-accelerator infrastructure. Open weight answers who can possess the model. It does not answer who can serve it economically. This is why the kernel result matters beyond a victory badge. Inference kernels, sparse communication, cache movement, quantization, speculative decoding, and serving topology determine whether theoretical capability becomes usable throughput. K3's advantage is not that benchmarks stopped being messy, it is that Moonshot exposed enough of the stack to examine where capability, latency, and cost meet, so the verdict should be plural. In one company case study, K3 matched Fable. On some public tasks it led. On independent aggregate evaluation, it approached but did not surpass Fable overall. In product experience, Moonshot says a gap remains. The benchmark courtroom does not issue one sentence. It releases a dataset with appendices and asks everyone to stop cropping the footnotes. The technical report also contains a cybersecurity evaluation, and this section needs a different tone. The goal is to describe capability and risk without reproducing operational details that would make exploitation easier. Moonshot divided its evaluation into vulnerability discovery and end-to-end exploit development. In the defensive discovery tier, the model examined current code bases and produced candidate vulnerabilities with reproductions. Moonshot reports that roughly 70% of the reviewed findings were genuine and that 16 previously unknown vulnerabilities were confirmed across 6 projects. The report describes serious examples in the Linux kernel, but the useful public conclusion is capability, not a recipe. The second tier required complete exploits in controlled environments. K3 solved 14 of 36 internal tasks, compared with 8 for GLM 5.2. 10 of K3's 14 successes were in user space software. Kernel exploitation remains substantially harder. Neither model solved 3/4 of that track. Human experts had verified that every task was solvable, giving the unsolved cases a meaningful reference rather than an unknowable ceiling. Trajectory review identified 4 recurring failures. The model could obtain useful primitives but failed to complete the final chain. Choose a poor strategy under mitigations, enter long, unproductive debugging loops, or submit without adequately verifying the deliverable. An independent assessment cited by the report found K3 stronger than GLM on exploit development measures, but reported arbitrary code execution on 0 of 41 tasks against harder end-to-end targets. These results support 2 statements at once. K3 demonstrates meaningful defensive discovery and some end-to-end exploitation capability. It also remains far below expert reliability on hardened targets. The report calls its measurement a lower bound because evaluations never cover every strategy. But lower bound is not permission to invent success beyond the observed tasks. Security capability is neither zero nor omnipotence. It is an uneven, operationally relevant distribution that requires access controls, monitoring, sandboxing, and repeated evaluation as models change. The report closes with case studies intended to show what long-horizon performance looks like outside a benchmark row. They are company-selected demonstrations, so we should treat them as examples, not population statistics. In GPU compiler development, K3 built Mini Triton, a compact Triton-like system with a domain-specific front-end, tile-level intermediate representation over MLIR, optimization passes, PTX code generation, and a runtime. Moonshot reports that it matched or beat Triton and Torch Compile on supported roofline workloads and sustained Nano GPT training with a loss curve close to the reference. The claim is not that one autonomous run replaced the compiler community. It is that the model assembled a coherent stack whose pieces work together, producing 5,000 lines that compile as coding. Producing a compiler that runs another training system is an argument. In chip design, K3 received 48 hours in open-source electronic design tools. It produced a simulated accelerator for a small model using the same broad architecture, targeting the NAND 45 nanometer library. Moonshot reports that the design fit within 4 square millimeters. Closed timing at 100 MHz contained about 1.46 million standard cells and 0.277 megabytes of SRAM, and simulated more than 8,700 decode tokens per second with INT4 arithmetic. No physical chip was fabricated. The result is a verified design flow inside a simulation environment. The recursive performance review has reached silicon in spirit and a netlist in fact. In scientific computing, Moonshot says K3 reproduced I love Q universal relations in computational astrophysics. The model reviewed more than 20 papers, implemented a numerical pipeline, evaluated more than 300 equations of state, found inconsistencies in published formulas, generated more than 3,000 lines of Python, and produced an interactive dashboard in about 2 hours. The blog compares that with 1 to 2 weeks for an experienced researcher. That time estimate is Moonshot's own framing, but the artifact demonstrates the intended workflow: literature, equations, code, validation, and visualization in one trajectory. K3 also performs strongly in Moonshot's web development and visual case studies. The report's blind internal comparison against Claude Opus 4.8 favored K3 overall, and most strongly on three-dimensional WebGL and shader tasks. The launch blog shows visual reports, dashboards, games, CAD work, video editing, and a motion graphics explanation of K3's own architecture. These examples align with the native vision training story, but polished showcases are selected outputs. A highlight reel is evidence that a capability exists, not a measurement of how often it arrives before lunch. Several catches remain. The model requires preserved reasoning history and can become unstable when a harness strips it. Moonshot warns that K3 may act too proactively under ambiguity. The company also states that user experience still noticeably trails Fable and Sol despite competitive benchmarks. Running the weights efficiently requires an accelerator supernode and specialized kernels. The license grants broad use but includes commercial conditions for large model-as-a-service businesses and attribution requirements for extremely large products. Open weight does not mean Apache license, zero infrastructure, or zero obligations. Quantization also changes what the model means. Expert weights are distributed in MXFP4, activations use MXFP8, and the training process adapts to that representation. A vendor implementation that silently changes precision, routing, caching, or preserved history may not reproduce the official behavior. The weights are necessary. The serving system is part of the product. This is why the kernel case study belongs at both ends of the episode. K3's headline capability emerges from architecture plus infrastructure. Then the model is used to improve part of that infrastructure. It writes kernels for attention residuals and KDA, the mechanisms that make its own depth and long context practical. It builds a miniature compiler and a simulated chip. Human engineers remain around the entire loop, choosing objectives and accepting changes, while the model expands how much of the loop can be expressed as an executable task. The recursive performance review is therefore neither fake nor autonomous self-creation. It is supervised technological bootstrapping. Software helps improve the hardware-facing software used to run better software. The employee committee has submitted its report. 880 experts were not selected for this token but would like the minutes to reflect that they remained available. So how did Kimi K3 nearly catch Claude Fable? Not by finding one secret neuron, importing one forbidden personality, or writing 2.8 trillion parameters on a slide until the benchmark surrendered. It improved information flow along 3 axes. KDA gives long sequences and efficient, editable memory, interrupted by global attention. ATNRes gives deep layers selective access to earlier representations. Stable LatentMoE makes an enormous expert pool trainable by compressing routed states, bounding activations, and balancing load. Native vision brings code and rendered output into one loop. Scaling law searches tune the model family rather than copying K2's settings. Post-training creates 9 domain and effort specialists, then distills them into one policy. Partial rollouts and agent env preserve million-token cognitive and environmental state. Quantization-aware training makes deployment numerics part of learning. Fleet scheduling and custom kernels make the resulting object economically callable. The result matches Fable in Moonshot's kernel study, approaches it on independent aggregate evaluations, exceeds it on selected public tasks, and still trails it overall and in user experience. That is more interesting than a universal victory. It means the open weight frontier is close enough that architecture and infrastructure choices can move it visibly within one generation. K3 did not build itself, but an early K3 helped optimize code used to build and serve its successor. The boundary between model capability and the engineering process around the model is becoming porous. The model is no longer only the artifact at the end of the pipeline. It can operate inside parts of the pipeline subject to human review, tools, sandboxes, tests, and the occasional kernel that would prefer not to be perceived. The final lesson is not that Fable has been defeated or that parameter counts have won. It is that frontier intelligence is becoming a systems discipline. The weights matter, the equations matter. The data, compiler, cache, sandbox, network, judge, harness, and accelerator matter. K3's technical report is 47 pages of one uncomfortable fact. The model is the smallest word for the machine we have built around it. 16 experts have approved this conclusion. 880 remain technically employed. The fictional Sahur alert has been closed as working as designed, which is how you know the system has reached production.